Hey guys, today we're going to talk about a new type of equation that you've probably never heard of before. So this is going into logistic models. Logistic models are used a lot whenever you're representing like a population or something like that, where in the very beginning there's initial rapid growth and it looks almost like it's exponential growth, which you can see on the left-hand side here. But at some point, that population has to stop growing because, like, the land can't handle it, or if it's talking about, like, the population of number of people who are sick in a school, then obviously you're not going to have more people sick than there are people in the school. So, what happens is this growth ends up leveling off at an asymptote, and that asymptote on the top is going to represent the carrying capacity. All of these logistic models are going to have two horizontal asymptotes, and that's what creates this S shape that you see here. And so the first horizontal asymptote is going to be at y equals 0. So that means there's like 0 people in the population that you're talking about. And the higher horizontal asymptote is going to represent the highest amount in the population that is possible. And so that's going to be called the carrying capacity. This is going to be what the equation for one of these logistic models looks like. This is not something that you guys have to remember at all. The number in the numerator, that's always going to be the carrying capacity. And then the R is a constant determined by the rate of growth. And so you're always going to be given that R value and then the B value that's right here as well. And the B value is just based on what the initial value was. So those are things that like typically you're going to be given the equation and then you're going to have to answer questions about it. So that's what we're going to do now. So here's our first example of one. And so it says on a college campus of 5,000 students, one student comes back with the flu. And it's talking about the spread of the flu is modeled by this equation, where y is going to be the total number of students infected over time. And then t is going to represent like how many days have passed. So it says the college will cancel classes when 40 or more students are ill. So first it wants to know what are the horizontal asymptotes and what do they represent. So we're always going to have a horizontal asymptote at y equals 0. So that's going to represent no students are sick. So I'm going to write no one sick. And then, we're also going to have a horizontal asymptote at the carrying capacity. So if you look back at your equation on this slide, the carrying capacity is that A value in the numerator. And so that is going to be, in this case, 5,000. So that's going to be our other horizontal asymptote. And that represents that everyone on campus is sick. So we're going to write everyone sick. And then B, it wants to know how many students will be affected after 5 days. So I'm just going to write B down here and start writing from down here. So for that, you would just have y equals, and you're going to have your equation. So 5,000 divided by 1 plus 4,999 e to the negative 0.8 t. And so then in this case, you have that equation and it says 5 days have passed. So you can go ahead and plug in 5 for t. And so you would calculate that. So I went ahead and typed that into our calculator here. And when I hit enter, it tells me about 54 students will be affected after 5 days. So 54 students. And then the last question wants to know, after how many days will the college cancel classes? So this is one where we have to set the equation equal to something. So it says that the college will cancel classes when 40% or more of the students are ill. So the first thing that you have to do is figure out how much is 40% of the students. So that would be, you have 5,000 students times 0.4, and whenever you work that out, 40% is going to be 2,000 students. So then what you need to do is set that 2,000 equal to our whole logistic equation. So equal to 5,000 divided by 1 plus 4,999 times e to the negative 0.8 t. And then to actually solve that out, my recommendation would be just to graph it and essentially put the 2,000 in for y equals in one spot and the equation in for y equals in another spot. And whenever I was saying spots, I was referring to separate equations, and I'm doing it on Desmos. If you're doing it on your calculator, you could have y1 and y2. So I'm just going to zoom out so I can see more of this graph. And then whenever it hits 2,000 students, you can see our line right there. So I'm just going to go ahead and try to find our intersection. It's not clicking onto it like I want it to right now. And so when y equals 2,000, 10 days have passed because it's telling me that x is 10.139. So that's how many days have passed. And then I was just going to see if we can zoom out far enough. And it's not very much of a curve on this one because the growth is so rapid, but you can see that it is leveling out up here at 5,000 as well. So I just wanted you to be able to see that horizontal asymptote. But to answer our question, we have this intersection here, and x is 10.139. So it would be after 10 days or during the 10th day, technically. So then our answer on here would be t equals 10 days. Okay, so I just want to quickly go through one more example. So in this one, a conservation organization releases 100 animals of an endangered species into a preserve. They believe that the preserve has a carrying capacity of 1,000 animals, and the growth is going to follow this logistic curve. So the first thing that it wants to know is what are the horizontal asymptotes and what do they represent? So for A, the first horizontal asymptote is of course going to be y equals 0. That represents like no animals in the preserve. And then my other horizontal asymptote is going to be y equals 1,000. And that represents the carrying capacity of the animals or the carrying capacity of the preserve. So carrying capacity. And then that also means there are 1,000 animals present. So the population on the preserve at that point is 1,000. For B, estimate the population after 5 months. It does tell us T is measured in months, so that is a plus. And on that one, you're just going to want to plug in 5 for T. So it would be 1,000 divided by 1 plus 9 times e to the negative 0.1656 times 5 months. And then I'm just going to type that into the calculator. So I've got it typed in, and then whenever I calculate it, it tells me there should be about 202.75 animals after 5 months. So I'm going to round that up and just say 203 animals. And then on C, it wants to know when the population will reach 500. So that's like C on the last one, where you're setting the amount that it's asking like when it'll reach equal to the equation itself. So we're going to do 500 equals 1,000 over 1 plus 9 e to the negative 0.1656 t. And then I'm going to go to Desmos and I'm going to put 500 in for one equation and then this 1,000 over ... in for the other equation. So I have my two equations typed in, and then I'm just going to have to zoom out to be able to see them. So you can see the intersection right here. I want to click on that second dot and it's at 13.26500. So my X value, which is representing time in this scenario, is 13.268. So if I come back over here, it wants to know when the population will reach that. So it's going to be after about 13 months. It's like during the 13th month. Whoops. There we go. After about 13 months. And then on this one, I believe if I zoom out a little bit more, you can see the S shape a little bit better in this one than you could the last one, but typically these graphs are going to have that kind of shape. A lot of them do have very rapid growth, so you can't see the actual curves that great unless you have a specific window set. But they do look like this S shape for logistic growth. And that's going to be about it. Your homework assignment for tonight is going to be just this 95 and 96. You don't have to worry about the other logarithm problems. I just want you to do the logistic growth models and let me know if you have any questions.